Welcome to Aerospace Structures 2. Today we'll be covering heat transfer, and I'll be focusing on thermal protection system later. But I want to point out that heat transfer is an very important area that needs to be considered in analysis of aerospace structures. And the reason we're teaching that in this aerospace structures class is that in a lot of problems, it is important to consider the thermal environments in the structural behavior of the systems. An example is a spacecraft. A spacecraft, when it's heated by this radiation from the sun, is going to get hot. And the spacecraft then will have to be analyzed to make sure that it can survive the thermal structural loads that it's going to experience in service. Another application of heat transfer is that heat transfer problems can apply significant amount of loading into the optics. We want to make sure those optics for spacecraft applications can work really well as well. For launch vehicle applications, heat transfer is also very important. You use insulation to protect the vehicle during ascent, and you also need insulation in the nozzles of the various engine components or rocket components. You may also have to analyze a few heat transfer problems related to when you're filling up the tank and when you're heating up the tank and things like that. So those are very important to consider in the design of thermal protection systems, in the design of material selection, and also play a key role into the structural design process. So that's why we're making this a priority to make sure we learn about the heat transfer. And while finite elements is a very well-known technique, I want to just kind of open it up and kind of give a very top-level view of what finite elements is really doing, because it is a true mathematical miracle. The finite element modeling or finite element analysis is an approximation technique that we can use. And that's used to discretize numerical solutions of various problems. And you can actually solve a lot of different problems: structural problems, heat transfer problems, moisture diffusion problems, and even finite fluid mechanics problems. So the idea is that when you have a partial differential equation which governs the physics of the problem, that partial differential equation has to be solved for a particular variable of interest. So in a heat transfer problem, the variable of interest is temperature. And that temperature can vary across in all three directions, okay? So that's the variable we want to solve for. In solid mechanics, structural mechanics, we're trying to solve for deflections in all the different directions. And once I know deflections, I can calculate strains. And once I know strains, I can calculate stresses. And once I know stresses, I can try to predict failure. And in reverse engineering, I want to make sure I design something so it doesn't break. So you can then thicken the sample. You can do whatever you want to do to make it work. Fluid mechanics. As fluid mechanics, you're looking at velocity of the fluid. You also have electricity and magnetism. And then you have problems where you can couple heat transfer with solid mechanics or couple a few of these things together. So what is the motivation behind finite elements? I think the idea here is to solve real problems because without finite elements, you're kind of stuck with hand calculations. Now, we're not against hand calculations by any means, but it is very powerful to be able to solve problems involving high amount of complexity, like an aircraft. An aircraft is highly complex to solve by hand. But if we can do some work with finite elements to simplify the modeling so I can get somewhere with it, why not? And so the finite element has a feature that no other code really has. It can be applied to any field problem. It can facilitate modeling complicated geometries. It can facilitate the application of boundary conditions and loads, and can deal with any type of material response. The finite element model, the good news, it looks like the original structure. And that's a cool thing. You can look at it in a computer. To increase accuracy of the solution, the cool thing is that all you have to do is to increase the mesh density. And I'll explain a little bit later what I mean with mesh density. So what is the goal? The goal in this particular example for solid mechanics is to compute the deformations, the strains and stresses, and the failure load. That is one objective. Or if you know what the failure load is going to be, what the limits of the structure, or the loads, you can then design it so that it doesn't fail at that particular load it needs to survive. The complex problems can really involve material and geometric nonlinearities. We're going to see that later on in this course. Large deformations and plasticity will both be discussed. We need to compute deformation, stress, and failure load. So here is an example of the partial differential equations that need to be solved. And there's a error here. This should be six equations. So we have 15 equations that are highly coupled. In the first equation set, we have equilibrium equations. In the second set, we have the constitutive law that relates the stress to the strain. And then we have the strain deflection relationships, where the strain relates to these deflections U1, U2, and U3. So how many equations I have? Here I have 3. Here I have 6. Here I have 6. I have a total of 15. And how many unknowns I have? I have 15. And so how do I solve 15 equations and 15 unknowns? They're highly coupled, and they also need to be solved over a complex domain. If you recall, when you took differential equations in school, that was quite complicated for a simple problem in a one-dimensional domain. Just imagine trying to solve this in 3D and it's partial differential equations and it's 15 equations, 15 unknowns. So what is the idea of finite elements? The goal of this course is not to teach the fundamentals of finite elements. That's taught in a different course. And I have a number of video lectures you can watch if you're interested in that. Or you can take a finite element course at your university. But right now what I'm trying to do, since finite elements will be a big part of what we're going to be teaching here, or using in the applications, because this class is an applied class. We're going to be applying some advanced concepts in finite elements to real world applications. And so that's why it's for me important that if you have not taken a finite element class, you at least understand the conceptual ideas behind them. So if you look at this CAD model on the left-hand side, I want to solve these partial differential equations. They are highly complex. They're highly coupled for these 15 unknowns. Well, what I'm going to do is something very simple. I'm going to take this domain and I'm going to divide it into subdomains, small subdomains, very small subdomains. And where it matters the most, let's say I'm interested in what's going on at the whole, then I'll increase the number of subdomains. And you can see very clearly, I divided a subdomain into triangles. I could have used quadrilaterals, for example. I could have done that, but in this case, I'm showing you triangles. Well, I'm breaking up that CAD model into simple subdomains, which I'm going to call those subdomains elements. So when I say I have an element, what I'm really talking about is these little subdomains. And these subdomains, the cool news is that I can have various element types. So finite elements basically is based on using subdomains that have shapes that can be used for breaking up the structure. So in 2D, I could have used this one or this triangle to break it up. Or I could have used even a more advanced element, which has mid-nodes and allows me to model with more accuracy, maybe this sharp, this circular hole, we can then put this triangle around that, for example, so we can get more accuracy. But it's more computation expensive. So you have to kind of trade which one is best for you. The point I want to make is, all I'm trying to say is that this CAD model is broken into small elements. And those elements that you see here, the beauty of this is that every single element here has different shape and it's not the same. However, there's a way in finite elements to take every element and map it into a standard element. And that element basically is where you do all the calculations. The cool news is that you can take these 15 equations, 15 unknowns, and try to formulate and solve it for that standard element. Once you have that standard element formulated, you can map it back into these irregular elements, because every single triangle here is not the same as that standard element. I can also do that with quadrilaterals. This quadrilateral here has a very random shape. And if I were to discretize this domain with quadrilaterals, every quadrilateral will look differently. But if I map it, I could map it into a square, which is incredible. And that square is what I will be using to solve these 15 equations, 15 unknowns. And so that's the good news, is that I can break with finite elements, I can divide the domain into small pieces. And those small pieces can be turned into standard element that applies to every single element in the domain. And using something called mapping, we're going to map a triangle to a standard triangle. And by mapping the geometry to a standard domain, what I've done, I've simplified the problem, and I'm now able to solve these differential equations by connecting them back together. You can see I can solve every triangle by itself, but then I have to piece it back together. And the locations at which the two triangles meet, you can see there a vertex, we call that a node. Locations where elements meet with each other. So for example, this triangular element has nodes, has three nodes, 1, 2, and 3 at each vertex. So this element will be, adjacent elements will be connected through these two nodes. So I'm gonna have a triangular element right here. And then for this here, you can see here it's highly curved. Well, I may have another element that's next to it, and these nodes are shared, these three nodes are shared along that edge. Okay, so that's kind of what we're talking about here. I want to make sure it's clear that this triangular element is of lower accuracy than this triangle element here with mid nodes, and the reason is because you have more degrees of freedom. So the polynomial because the solution of partial differential equations is really accomplished by assuming a polynomial distribution that's able to basically approximate the solution to the triangle. And the same thing goes for this one here. So the triangle here on the right hand side has more nodes, so you're going to have a higher order polynomial that's going to be better at capturing the response of that triangle. And in addition to that, square elements have more terms. I have four nodes, so I have four terms in the polynomial approximation compared to 2D. 2D has only three. So I'll expect the 2D element to be a little bit more accurate than a triangular element. And when I go to mid-side nodes, I have even more degrees of freedom. So therefore, I'll expect even more accuracy. But that's not always the case, and you have to do a study to figure stuff out. So this process of taking a CAD model and converting that into subdomains as you see them here, we call that the pre-processing stage. And then I have to configure the model. What do I mean with that? That's also pre-processing, by the way. I'm going to apply the loads at these nodes. I'm going to apply boundary conditions. So say it's clamped at the very left end. I'll take those nodes and fix them. And I will apply material properties. I'm going to say, okay, this is steel or aluminum. I have to tell the software that what this material is, and I'll specify to the software what those properties are. And then this is where the magic happens. We solve the system of equations, and this is the insane part of finite elements. I'm taking a very complex problem with 15 equations and 15 unknowns, and I'm taking that and simplifying that into a stiffness matrix times the deflection equals an external force. And this is a very simple thing to solve for. And what this is going to give me is the deflections at every node you see here. Beautifully done, because now I can take that and plot that directly. So I took a highly complex partial differential equation for a very complex, it's actually complex, not easy to solve, not complicated, for a domain that's not easy, and I'm solving them, and that is going to lead to simplification, which is a linear algebra problem, KU equals F. All I have to do is invert the stiffness matrix, and I can solve for the deflections. Once I know the deflections, I can solve for strains. Once I know strains, I can solve for stresses. We can do this, and now that I know the deflections, I can plot the deflections, I can plot the strains, I can plot the stresses. What's plotted here is the stresses, for example. I can do dynamic modeling as well. We'll be doing a lot in this course. We're going to be doing steady-state dynamics, random vibration. And so the idea of finite elements is quite powerful because I can solve problems I couldn't do before. So in finite elements for solid mechanics, what are the different aspects that come together in the big picture perspective? You're trying to make sure that you have a sufficient margin of safety for the system. And so that implies that you have the CAD model, that you're given the composite layup, the stacking sequence, you're given the limit loads, the temperatures, external loads, all the stuff you need, that you've identified all the critical failure modes, and that you have measured all the properties for all the different constituents, the composite, the foam, the metal, everything you need. That goes as an input into your finite element model. All the elastic properties, the modulus, the Young modulus, the Poisson ratio, the composite layup, the geometry, the limit loads, you measure it. And here you can see that I've divided a subdomain using these solid elements here on the very bottom right. 3D solid hex elements, we call them, has 8 nodes. And so it's very nicely meshed. And then that is then what we're going to do now is solve this 15 equation, 15 unknowns by approximating the subdomains into polynomial, using polynomials. And that what allows me to do is allows me to simplify the problem to ku equals f, which allows me to then plot the stresses very easily. And then I can now validate my model to make sure it matches the test. If it doesn't match the test, I have to make adjustments to my model to see what I got wrong, because analysis does become important. Is the analysis what provides the transfer function between a test on the ground and something that's flying. And now I can use the finite element results to provide the margins of safety for the system if you know the factors of safety for the given program. When you look at more advanced applications of finite elements as applied to airplanes, for example, you're going to have to really be smart about how those are applied. And typically, in a large company that's working on an aircraft, you could have various components of the aircraft being provided to the various people within an organization. So you could have person A works on the wing, person B works on the tail, and what you want to do is have a way of connecting everything together. So there is some amount of coordination to make sure that the models can be assembled into one big model, because as I will discuss later, dynamics becomes very important. We're going to derive loads based on dynamics and then apply those loads into static models to gain more confidence in what we're doing. Finite element applications have been used quite significantly. For example, you have the American Airlines Flight 587 accident investigation where the tail broke off and the aircraft crashed. That's an example of where you could then study the area of concern by refining the mesh. And when I say refine the mesh, is to increase the number of subdomains, make it smaller, make the elements smaller, and increase the density of them to increase our understanding of system performance in that location. So in general, you have a physical phenomena, and I hear what I've discussed with solid mechanics, but you have a physical phenomena, solid mechanics, fluid mechanics, thermal conduction, diffusion, electrical conduction. And then I have a set of governing equations for each of these guys that describe that physical phenomenon. That's your mathematical aspects, right? But my goal then is to use polynomial approximations to then be able to turn these governing equations, which are a pain to solve by hand, and turn them into a linear system of equations, and can be nonlinear as well, but generally linear for 90% of the problem. And you have the stiffness matrix times the nodal vector times the force vector. I can solve for this value here, and U here could represent, in this case, could be the deflection. In this case, could mean the flow velocity. In this case, could be the temperature. In this case, could be the moisture concentration. In this case, could be the voltage. So you can solve for those variables for the variable of interest. Now, here is an example of a 2D heat transfer problem. And you can actually look it up, the solution to this. Very, very interesting. If I have this square, and look at how simple the problem is, by the way. Look at how simple the problem is. Say that the temperature on this edge is 100, and on this edge is 100, and on this edge is 100, and on this edge is 400. Well, the solution is actually not that simple. And the analytical solution looks like the one at the top right. Now try to do that for like an aircraft or a spacecraft which has hundreds of components. That's not tractable. We don't want to do that. we want to figure out a way of taking that partial differential equation, which you see at the top left, which is the Laplacian, is Laplacian of the problem. And I want to take that, take this domain, which is actually simple, actually. You will think that it's easy to solve, but clearly it takes a very complex analytical solution. I'll take this domain, divide it into subdomains, triangles, and then I'll take that and turn it into kt equals q. K is known, q is known. K depends on the geometry, depends on how many elements I have, it depends on the material properties, and so forth. Q are the heat fluxes I'm applying or the temperatures I'm applying. But I can solve for T now, and when I solve for T, I can just plot it. That's the beauty of finite elements. All I have to do is mesh, apply the properties correctly, plot the results, which is extremely powerful. And it allows us to study problems that would have been otherwise very difficult to study. So the basis of finite elements is really the development of approximate solutions to partial differential equations, in summary. And the chief motivation of lectures that you may have seen in finite elements is to really show how to put everything together. So we're going to really look at the application to heat transfer today, to 3D and 2D conduction, 1D conduction and convection. We're then going to move to TPS, thermal protection systems that are used quite extensively in aerospace applications. So let's first study the heat transfer balance. What's going on with the heat transfer balance? I think it's an important consideration that needs to be we should take a look. So I have a heat source or sink Q. So that's my heat source Q. And notice how that's integrated over the volume. And that has to be balanced somehow. It needs to be balanced by the heat flow per unit area, per unit across the surface. So somehow, whatever heat generation I have, or heat source or sink I have within the volume, has to be balanced by anything coming out. And that's, you can see here is Qn as an example. So if I look at a heat flow vector, so you can see here the heat flow vector Q is going to have several components. But the normal component is Q dotted with a normal vector at that surface location. So Q dot N gives me the normal to that surface, and Q bold is basically for two-dimensional QX, QY, for three-dimensional QX, QY, and QZ. So this right here has to be fully balanced with what's going on at the surface. So that has to be equal. That's a volume integral, but whatever is occurring as a heat source or heat sink inside the volume needs to be equilibrated by what's going on the surface. That's really what this is saying, telling us, and I think it's important to discuss. There's something very interesting here that needs to be discussed further, and that's Fourier's law. What it states is that the rate of flow of heat energy per unit area through a surface is proportional to the negative temperature gradient across the surface. In other words, the heat flux or the rate of flow of heat energy per unit area has to be equal to some constant times the negative of the gradient of temperature. And this D here happens to be the constitutive law. It's the constitutive law that tells us how quickly a material heats up or how slow it heats up. For example, heating a cork should take longer than heating aluminum. That's taken care of by D, okay, that constant. And that can be measured using experimental observations. So Q bold equals this matrix here, and you can see here I have KXX, KXY, and KXZ, and so forth, because for composite materials, you could have a different conductivity in each direction. Now, for isotropic materials, you'll most likely have K as a diagonal, K, 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 and then you have 0 in the off diagonals. And K represents the conductivity of the material for isotropic materials, and in this case, it's fully anisotropic. Now, I have to take the gradient of T, and the gradient means this. If you've never seen it before, that's a gradient of T. The gradient, the definition of gradient. This gradient is applied to T, and this multiplication is what gives me the components of the heat flux on the surface, Qx, Qy, and Qz. So when I go back to the definition, I have Qn, which is Q dotted with N. Then I can substitute what Q really is, which is d gradient of T, and I substitute it here, and I get Qn equals that. So with that said, and so we want to convert the right side of, we want to convert this equation into volume integral. Right now, this equation is unusable because here I have a volume integral, here I have a surface integral. Or I have good news for you. We can use a Gauss theorem or Stokes theorem, one of those theorems where you can convert a surface integral into volume integral. And when I think about that concept, what I'm really talking about here is integration by parts. You may have seen that in calculus. I like to call it integration by parts. The gradient dot q dv equals the gradient transpose q dv. And so I'll integrate parts by pretending there's a 1 there that's not there. I'll put 1 on the left side, gradient of transpose q, and then I'll draw an arrow here, plus n. I'll remove this gradient but pass it to the 1, and the gradient of 1 is 0 because the derivative of 1 is 0. So what I'll do is I'll multiply this cross term and put it in the boundary. You can see that there. That's a boundary, q dot n. You can see that in the boundary. So what is the boundary of a volume? The boundary of a volume is a surface integral. So that's what you see there, right? And then the gradient of 1 is 0. So 0 times q is 0. And you can see that there. So I'm teaching you Gauss theorem. I'm teaching you how to do it without memorizing the theorem. But yeah, that is how I do it myself. And so now I have a way of converting this surface integral into a volume integral. So this must be equal to that. That's the meaning. So because I'm able to do so, and it's a mathematical miracle also, because this is telling us if I know what's going on the surface, I know what's going on in the volume, which is quite incredible, actually. So I can substitute this term by that term. And I can put everything on the left-hand side. And when I do that, I get Q minus gradient of Q. Now, I know what Q bold is because Q is a heat flux on the surface, which I have found to be d gradient of T. And I can then plug it in here because Q is d gradient of T. And because this has to be true for every point in the domain, the partial differential equation governing the behavior for heat transfer problems is just essentially the heat sink or heat source plus the gradient transpose D times the gradient of T. And there's a single equation here, just one equation. This here is a 1 by 3. These are 3 by 3, and these are 3 by 1. So you get a single equation there. And the idea is to specify either the temperature at the surface or the heat flux at the surface. We can extend this to 3D. I mean, I showed it for 2D here. We can extend it for 3D very simply. The 3D version looks like this. And when if I assume that the off diagonal terms are 0, the equation for heat transfer, only considering conductivity and considering temperatures applied on the surface in some sections of the surface with heat flux applied, gives us this equation here, which looks a lot like the Laplace equation. So this is the equation we want to solve for heat transfer problems. T here is the unknown. Everything else is known. Kxx, Kyy, and Kzz are the conductivity of the material, which can be measured in the lab, and Q is a heat source or heat sink, which is known as well. Okay? So continuing on, I'm going to call this the strong form of the problem. And so continuing on here, we're going to be looking at some advanced concepts on that. Let's look at steady state heat conduction. So now you could have conduction on the side. You have, and this is just 1D, right? I covered the more complicated 2D and 3D, but to show you in 1D, if I have a rate of heat from the surroundings, I can do a little cut here. So this H, the heat flow rate, and this H plus DH. The area is AX, the area DX away is AX plus DX. And here I have my heat, the heat transfer from the surroundings. I can take this free body diagram and kind of write it out. So H plus Q dx. So this H plus the heat going in, Qx dx has to be equal to H plus dA, H plus dH, right? So that's heat going in and heat going out. So that has to be equal. And you can see here that I can now cancel H, and I have then dH dx equals Q. The heat flux then becomes, if I look at it in terms of area, cross section, then I have a heat flux quantity, and that will be Hx equals A times Q, right? The area, cross sectional area. So I can now substitute this heat flux, this quantity per unit area, into this equation. So I get dAq divided by dx, or respect to x, equals Q. A is known because that's the area distribution, and we're just trying to figure out how to now proceed from here. The one-dimensional version of this is that Q equals minus K, which is the conductivity of the material, dt dx. And so now I can plug that in into this equation to fully get the steady state heat conduction problem for 1D. So now all I have to do is solve this. This one is easy to solve. You can integrate it once and twice, and you can solve for T. It's a polynomial, quadratic polynomial. So this is the same thing we saw here. It's actually almost the same. If I wanted to look at 1D, I just cancel, just turn this term to zero, turn this term to zero. And this equation, the first term and the very last term, is in essence what I have here, in essence, if you think about it. Okay? And I forgot to mention, I was applying conservation of heat in equals heat out. So that's the key there that I think is quite straightforward. So I could have boundary conditions that are interesting. For example, I could have this, I could have the boundaries to be related in some ways to, I could have boundaries that are subject to convective heating, for example. The effects from convection. So assume you have convection on the side, right? There's convection on this side because there's a fluid surrounding the structure. Well, you see this term Q here. That term Q is a heat transfer from the fluid into the structure, for example. So I can take that Q and figure out what to do with that Q. That Q can be calculated very easily. So that Q is going to be defined as HP times T minus T of the fluid. And H here is the heat transfer coefficient, and P is the perimeter. Now, the perimeter of that particular location. What's interesting here is notice if the temperature of the structure is the same as the fluid, then this term vanishes. And so there's nothing going on in terms of transfer of heat from the fluid surrounding into the material. But this formula here is really accounting for convection. So if you have a hot fluid, that hot fluid is going to push the temperature of that structure to get hotter, so that it reaches equilibrium and it becomes as hot as a fluid. And when that happens, I will assume that the temperature distribution across the whole thing is likely to be TF. The temperature of the structure will become the same as the temperature of the fluid. Hopefully, over time, I'll think that will happen. For example, if you have a very hot cup of ice, sorry, not cup of ice, if you have a very hot cup of coffee, that makes more sense, and it's sitting out there, then the temperature of the cup of coffee will drop so that it matches the temperature of the room that you're in. Now, what is causing that? What is causing that change in temperature is really convection. Is the convection the fact that the cup of coffee is surrounded by a fluid, and that fluid is air, and that air is at a room temperature. And so this TF is, say, 77 degrees Fahrenheit, while the temperature of the cup could be 120 degrees Fahrenheit. And so this temperature over time will approach the film coefficient or the fluid coefficient. I'm sorry, the fluid temperature. I apologize. H is a material property, or almost like a way of calculating how this H could impact. So the greater H is, the more the transfer of heat or out, heat going out or in from the fluid into the material. For example, if I have a coffee cup and I have a convection oven, and I put the coffee cup in a convection oven and there's no air moving, that should take lower time for the cup of that should take longer time for the cup of coffee to warm up compared to a situation where the convection oven is blowing hot air at very high speeds into the part. So to the question that was asked earlier, how to account for convection, for example, or for vortexes, these where vortices could come into play. Because if you have vortices, those vortices are going to increase H, and H is going to increase the heat transfer. So H is where the fluid mechanics is embedded. That's where you want to figure out what H could be. But that's kind of what we're talking about here is how to solve different steady state heat conduction convection problems in this case. So we went from 1D conduction to 1D steady state heat conduction convection, right? And so I'll keep moving along. I want to show the analogy between heat transfer and structural analysis problems. So in a structural problem, you're looking at displacements. Temperature is analogous to that. Stress and strain, the analogous to that is heat flux. Displacement, the analogous to that is fixed temperature. Displacement boundary conditions, what I meant there. You apply surface traction. In heat transfer, you apply a heat flux boundary condition. In structural problems, you have body force. In heat transfer, you have internal heat generation. In structural problems, you have the Young modulus. And in heat transfer, you're looking at thermal conductivity, the K, and also the H for convection problems. How efficient, basically the question being asked there is, how efficient is the fluid able to transfer the heat in or out from the structure? That's what that H is saying, right? Because if H was zero, clearly there's no heat transfer between the fluid to the structure and vice versa. So H, the higher the H is, the more transfer is going to occur, and the faster potentially. So that's what the H is telling us, and that's what that's about. So yeah, just to summarize, heat transfer can occur from the surroundings to the boundary, and I already covered that. The convection coefficient typically has these units of energy, and then area, and then temperature. So those are the things you're going to be seeing moving forward. So I cover that. We cover that, and I can add more terms. So I can even add more terms in case I have radiation or something else. But the bottom line is that I have the heat conduction convection problem in this equation here. K is the conductivity of the material, A is the cross-sectional area, T is the temperature, H is the heat transfer coefficient, P is the perimeter, T is the temperature of the structure at the surface, T infinity here is the fluid temperature, and then A is the cross-sectional area, and Q is the heat input. I could even apply other types of heat inputs. And then I will have boundary conditions that are specified. And so what I want to talk about, I don't want to go into the nuts and bolts. I don't want to go through every single thing and how to formulate finite elements. But I want to kind of show you the basic premise. So you have this equation. What you do is you take this equation, multiply by some sort of function, which I call V. So that's kind of the step that people take when they want to approximate the solution to this partial differential equation. This is covered in more in advanced course. This course is advanced course, but we're looking more at applications. So in this particular lecture, what I plan to do is cover a very top level mechanics of how this equation can be discretized into the mathematical miracle of a linear algebra problem, where I can solve for temperature by just simply inverting the stiffness or the conductivity matrix, and yeah, just simplifying the problem to that extent. So what I've done here, I've written this again, and I multiplied by V, and I integrated this over the domain. I call this the weighted residual. That's what we call the problem where formulated in weighted residual, multiplied by some orthogonal function, v, that is unknown. And then the idea is to integrate by parts in a manner such that the number of derivatives here for the primary variable of interest, which is temperature, is shared equally with v. So we're just only doing the integration by parts on this first term, not the second or third term, because they don't have derivatives. So to integrate by parts, very similar to what I showed earlier, write v on the left side, put this on the right side, remove a prime, and put it on the left side instead. And now I do a cross plus minus. What's at the bottom of this integral goes back inside the integral like that. It replaces that term. You can see here kat prime times v prime is exactly that. And then this cross term becomes your boundary term. This is exactly what's occurring at the boundaries, while this is occurring inside the boundary. And we call this the weak form of the problem. And I know I'm throwing a lot of ideas at you, but again, what I'm trying to do is explain how finite elements, is derived from a very simple mathematical principle. And this thing is called the weak form of the problem. And why it's called the weak form of the problem? Because I took two derivatives and got rid of one of them. And I've weakened the continuity requirements. For example, if I have a linear function for temperature, the second derivative of a linear function gives me 0. So a quadratic function, second derivative of that gives me a constant. So you can see that by lowering the order of differentiation, what I've done is I've weakened the continuity requirements. Now the temperature could have a linear function, and a derivative of a linear function gives me constant. While here, in the original premise of the problem, t double prime disappeared because the derivative linear function is 0. So that's the benefit of the weak form, and it allows me now to use approximation functions. Polynomials are very simple, like linear functions and so forth. And I don't want to go into more detail here. Bottom line is, once I have this weak form derived, now what I need to do is to derive a polynomial approximation of some kind. And I know you see a lot of numbers here and it looks very confusing, but just bear with me because I think it's simpler than what you will think. So these polynomials are selected in a very smart way. They're selected so that the unknowns, the temperature unknowns, are right at the nodes. So say this is a single element, and the unknowns for this polynomial approximation are going to be these coefficients, ti, tk, and tj. These polynomials are selected very carefully. All these kx, jxk, all these are numbers. So you don't have to worry about that. These are all numbers, and all I've done is approximated the solution over this domain. I've approximated solution over that domain using these polynomials. I'm just giving you the formula so you can see what it is. And you can see that these polynomials vanish at a particular location. For example, this polynomial clearly vanishes at j and k. For example, if I put xj for x, this goes away. If I put xk for x, this goes away. So this polynomial is 0 at that node and that node, but this polynomial is 1, it has a value of 1 at the node of interest, ti. You can see that if I put xi here, xi minus xj cancels out, xi minus xk cancels out with this, so I get 1. So these polynomials are carefully chosen in such a manner that I recover the temperature at that particular location, which is incredible idea. So once I have this temperature approximation over that domain, I'll then proceed to plug it in. I'll plug in this approximation into this. And here, t can be written as the polynomial approximations times the vector of temperatures. They're all known at the nodes, okay? And I'll then notice how I had to take these derivatives, this ka, t prime, v prime. So I'll take the derivative here, t prime, and t prime is just the derivative of those polynomials. T are constants, I don't know them, so I get b times t. I'm gonna call this whole thing b bold. Now I'm ready to substitute these things into here, and all I'm doing right now is anytime I see t, I'll plug it in for n bold, t bold. which is basically these polynomials times these unknowns. And you can see for t prime, I plugged in b bold, t bold. And then for v, I'm going to plug in basically, uh, yeah, for v, I'm going to plug in t, right? So then I have the same thing here. I have t, I plug in nt for that. And then for v, I'm going to plug in n, which, so v, let me remind you what v is. V is this function that I multiply the whole thing with. And this function is unknown. But I'm going to select it to always be these polynomials. Okay. And so when you do the math, what you get is here, this equation here at the bottom. AQ times V, and V is the polynomials, right? So we're going to select the polynomials as the thing to be plugging in. Here you get B because the derivative of V prime is really, V is these polynomials, but prime of that I call it B bold, and that's why you see V to be put as B bold here. So very beautiful, done. Now I have this equation that's true for one element. And this term corresponds to conduction, this corresponds to convection. And the idea now is to do this for every element and then assemble all the elements together. Now, this course is not about going to the theory of finite elements, but I think it was very important to kind of show you how things work out if you were to start from first principles. So it's stuck in your head as you're using finite elements in the various problems that will be applying these to. So what we're trying to solve for is this T, Ti, Tk, Tj. These are the temperatures at the nodes. Guess what? I know this whole thing. These are numbers. You don't have to worry. K, the conductivity is known. A is known. The integral over the polynomials is known. So these are all numbers, and this is going to give me a 3 by 3 matrix. All these are numbers, and the heat fluxes are numbers. So you can now invert this using linear algebra or MATLAB to get the temperatures of the nodes. That's the beauty of that. As an example, we took a partial differential equation with just 2 nodes. And guess what? After you apply the process I talked about, you get a very simple matrix times Ti, Tj, the unknowns at the nodes, the temperature unknowns at the nodes. And all you have to do is now invert this. Given the heat flux, you can then solve for Ti and Tj, the temperatures at those nodes. Here's a quick example. Calculate the nodal temperatures of 4 elements while maintaining 200 degrees C. So you maintain this at 200 degrees C over here. The area, the cross-sectional area, so assume this is like a tube. The cross-sectional area is 1 meter squared, the length is 1 meter, and the conductivity of the material is given here. The heat enters at node 2, so we're going to enter some heat here at 500. The heat goes out at node 4 of 200, and so the question is, what is the temperature across the tube? So then you write the equations for each element. I have 4 elements, so this is my domain, and I've divided the domain into 4 elements, so I should have 4 of these guys. 1, 2, 3, 4. I won't go into the extensive details on how to assemble it, but you will assemble these 4 elements together by knowing that they're shared at the nodes. And when you do that process, and you can see here, element 1 is made up of temperature T1 and T2. Element 2 is made up of temperature T2 and T3, and so forth. So T2 is shared, you can see that there. And if you were to put it all together into one single equation, it's going to look like this. These are all numbers, and now all you have to do, I know the heat fluxes at the boundaries of the nodes. Q1 is not known, Q2 is known, it's 500, Q3 is 0 because there's no heat flux coming in and out, so that's 0. Q4 is 200 out, Q5 is 0 because I have nothing going in or out. This one is unknown because I'm specifying the temperature, so we don't know what's going on with that one. But for the rest of them, I know what's going on. So now all I have to do is solve for T2, T3, T4, T5, and Q1. And when you do that, you get the temperatures across all the nodes in this problem. So listen how we took, look at how we took this problem, this differential equation, and we solve for temperature by using linear algebra, right? We solved it just using this. And how I know what the temperature distribution is across the element Well, I told you that I know that a polynomial approximation across it. So if I know T1 and T2, then I can determine what the distribution of temperature is across these two elements, two nodes. Here is yet another example of four-element solution for a situation where uh, there is no heat flow going out and this wall is infinite in this direction. So in other words, there's no heat flow out here and I'm fixing this at 200 degrees F. So the question is, what is the temperature distribution? I can divide again the domain into four elements. Same process. I just use the same process, and I can solve for temperature. I can solve for temperature very, very easily and very quickly. And I won't go into the specifics because the whole point of this is to kind of give you the big picture perspective. So in summary, we have the boundary value problem for 2D and 3D. This was for 2D, this for 3D, and this for 2D. Sorry, this is not for 2D. This is for everything. And this apply to 3D and then apply to 2D, which I already covered in extensive detail. Okay, so with that said, so now let's look at how we will consider a time-dependent problem. So in a time-dependent problem, you're going to have to consider the specific heat of the material, the density, and you have to add this term dt. So the temperature has a derivative now with respect to time. And now you have to consider the density and the specific heat of the material. And now this equation now has to be discretized just like I showed before. Multiply the whole thing by V and integrate by parts as shown here, as I did before. And once you do that, you get this equation. And this equation is now valid for a time-dependent problem, like an unsteady behavior. So before we're looking at steady state where it's not dependent on time, here we're looking at how things could evolve over time. So you can develop now the weak form using the process I discussed before in 2D. This is for 1D. In 1D, you get this. I'm sorry, this is not for 1D. This is for 2D. And now this is shown what the weak form is in 2D. And I'm kind of skipping some of these details because the bottom line is the same process before, but I'm keeping this term now. I have this time-dependent problem. Now, if I had a steady state problem, this one goes away. But in our case, this stays here and has to be looked at carefully as we move through these derivations. This V shouldn't go here, that's an error. But in general, everything looks pretty good. And we just substitute everything we talked about before. And the weak form for 3D becomes this one here. And I already have another video in Finite Elements that goes into extensive details on the discretization problems for finite elements. But here we're giving a top level view and not going into extensive details. And again, V is an arbitrary function. We're selecting V to be the polynomials that can solve the problem within a domain, within an element. D is the conductivity matrix, and T is what we're looking for. Okay? So there you go. And so now what we want to do is discretize the domain. So say I have a domain of some kind, I could discretize using 2D elements like you see here, triangular elements, and so forth. And we're going to discretize this equation over a single element that gets mapped into a standard element. So here's an example of a transient problem. You have a transient problem of some kind where this is equal to 0. I have some initial boundary conditions. I can approximate the behavior over a single element by multiplying this partial differential equation and making it orthogonal to a function v. So I'm multiplying this whole thing by v basically. And what I'll do is I'll integrate by parts by removing this derivative and transferring over to v for this term, because this term has equal derivatives on v and w. So as a consequence, I don't have to worry about this term. And I'm trying to weaken the continuity requirements. So when I integrate by parts, I apologize, I get this here with the following boundary conditions. And so if I look at a single element, I can approximate the behavior of how W varies between this point and this point. And I'm going to select this polynomial. It should be linear because I have only two unknowns. You can see that it works out because if x is xj, which is this point here, I get 0. And if x equals xj, then this becomes the length of the element, xj minus xi. Le divided by Le is 1. So clearly W is wj at x equals xj. So that works out. You can see that this polynomial works out. You can also see that now what I'm doing too is I'm varying the nodal deflection, the nodal values, not deflections, I apologize. The nodal values, I can vary them over time. You can see that there. So that's now varying over time. Before these were constant. This was not varying over time. Only we had Wi and Wj and they're not varying over time. But now they do. And you can see that we're applying separation of variables here. We're separating the time domain from the spatial domain. I can again put this in a matrix where n is a polynomial here, this first polynomial and second polynomial, and d bold is made up of these two quantities here. We'll then substitute this equation. So for W, we're going to select n times d, and for V, we're going to substitute n. So that's what I've done for this equation. We're going to take this n times d and just plug it in there and see what happens. And when I do, when you look at all the things that need to be considered in this derivative, W is just n bold times d, so that's easy. Derivative of W with respect to x needs to be calculated. You can see that here. So when you go through that, this becomes b bold times d. And then you have the derivative of W with respect to time. That's easy. That's n bold times d dot, where now these derivatives are the ones that are being looked at. And now I can go ahead and substitute it. And when I do so, and I invite you to do it at home, so you can see that I can go from here to here. And any group that derives it going from here, from this step, if you can derive going from that step to this step, I'll give you 50 points towards, or if you're able to do it, we can come up with an agreement of extra points that can be applied for issues you're encountering. But the point I want to make is that this is very easy because all I've done is substitution. Just substituting these guys in here. And for V, I'm going to substitute N transpose. So when I do that and I solve for this N1, Ni, and Nj, when I'm able to substitute to that and integrate it over this integral, what I actually get is are just basically numbers. This is what I get. It's very simple. For a single element, it looks very simple. Now what I have is, I think you've seen before how to solve time-dependent problems numerically. But this is the equation that we're looking at now. Very simple now. Looks very simple for single element. But now I have to look at, say I want to discretize the domain into 3 elements. I have this domain. All I have to use this equation 3 times. LE is 1/3. You can see here LE is 1/3, so I get 1/18. And that's 3. Because LE is 1/3, so I get 3 there. And yeah, that's element number 1, element number 2, element number 3. Now notice that if every element is the same size, every single of these are the same. Nothing changes, which is amazing because that's cool. I don't have to keep doing these calculations over and over and over if the element size is the same. I can then assemble these equations into a mega equation because you can see here that I have this for node 1 and node 2, but element 2 is node 2 and node 3, and element 3 is node 3 and 4. So there is a way to bring everything together, and when I do that, I get this 4x4 matrix. I apply the boundary conditions. I know them. They're given to us in the initial statement. They're given to us here. W at x equals 1 is 1, for example. So I can just substitute everything here. And now I can then basically, yeah, so I basically simplified the equation into this, right? W1, W2, W3 are the unknowns. And now I have to do is to do is, now I have to do is do a solution to this, which is using finite difference. So if I call this C bold, this K bold, and this F bold, and I put this into D dot, and I put this into D. So now that I have these equations, these three equations, I'm ready to solve for W1, W2, W3. And to do that, we're going to use an idea called finite difference. And what we plan to do is then take this is a time derivative, dt. And so I'm going to approximate the solution as the solution in the present minus the solution in the past divided by the time step when this occurs. And so I plug that into this d dot, and I have this di, I'll leave it alone. I can now solve for di, so I basically get di equals all this. So in other words, if I know the solution in the past, if I know the solution in the past for w, and I know c, I know k, these are all numbers, then all I have to do is plug everything in, and given the time step, I can calculate the values of d presently, meaning I know w as a function of time. So that's the idea here, is to march the solution forward once I know the initial conditions. And so here, I don't want to go into the extensive details, but you can see here the equation is given. You can use the recurrence formula. Once you know the initial state, the initial value of W, you can then time march the solution to get the future solutions. And you can see here it was done here. Say you start with the initial value of 111 at time equals 0. You can see how quickly these are all numbers that basically end up being very simple. And so as a function of time, you can now get the evolution of W as a function of time. There's more advanced ways to use the recurrence formula, but in general, the backward difference method works really well. And I don't want to bog down this particular lecture, because this lecture again is not about the theory of finite elements, although I'm covering some aspects very top level so that you know how that works. So there are various methods. The method I showed you is called the backward difference method. There's a forward difference method. And so this equation here allows you to look at various formulas like that. So this is your forward difference method in this case. And then here, and I'm moving quickly, you can pause the video and look at it later. We can look at more advanced techniques. Like if I put theta equals 1/2 in this formula at the top that I gave here, this one here, 1/2. So for theta equals 1, you recover exactly what I showed you here in the previous, this equation. That's a backward difference. If you put theta equals 0, you recover the forward difference method, which I'm not covering here. And if you put theta equals 1/2, you recover something called the central difference method. And you can then time march the solution just like I explained. Nothing too different. So if we look at an unsteady heat conduction problem, we can look at that and say I have this problem with these boundary conditions, and the problem is really looking at cooling of a 1D bar that's initially heated to have a parabolic distribution with a maximum temperature being at the center. So we can look at that for 5 elements, and again use the same formulas that we just discussed. Multiply this by V, so take this multiplied by V, integrate it by parts, and you will get this. And if you don't remember how to integrate parts, look it up in a calculus book because it's explained there, or use the methods I described today. So you get this equation, and now I approximate the domain using a linear function, simple linear function, and this works really well. You can check it yourself at home that when I put x equals xi at this node, I should recover the temperature at this node, and you will see that it does. If I put xi here, I get LE divided by LE, I get 1. If I put xi here, I get 0. So I do recover back that value. If I put x equals xj, this goes away, this becomes 1, And so I recover this temperature becomes TJ, which is that point. And anywhere in between, X can be anywhere between XI and XJ. And this is going to be, the temperature in between is going to be a combination of something here plus something here. I'll put this into T and these interpolation functions into N, these polynomial approximations. And then I'm ready now to, again, to execute. I can find this, I can find this, I can find this, and plug it in. So that's what I've done here. Plug it into the equation, and now evaluate the integrals, and you get this for a single element. And then since each element in our case is of size 0.4, and I stated it here because I said it was 5 elements going from -1 to 1. So clearly, the length of the element has to be 0.4. So L is 0.4. I plug it in, and I get this as, which is true for every element, this equation here. I can then assemble it because the nodes are shared across element boundaries. And when I impose the boundary conditions, the boundary conditions, which are the temperatures, I get this. And now I can reduce the system to what matters, what I want to solve for, because I already know this T1 and T6 and T1 and T6. So all I don't know is T1 through T5. So now I'm ready to apply the idea of the forward or backward difference, whatever appetizes you to look at. Yeah, so you can then time march the solution. T equals 0.1, I get a certain temperature, and then I plug that in again, and I get a new temperature at time equals 0.2, and so forth. So I can time march the solution. This was done in Abacus. You can see here the nodal values are provided, the elements are provided. That's the element type within Abacus. That's a one-dimensional heat conduction element. The 2 means that it's a two-noded element, so very simple. Here's aluminum material, so the conductivity of the aluminum is provided, specific heat, and so forth. So all that is provided here, and the step here, what it does, it basically time marches a solution and solves it. All this you can do through a GUI, so it's not really important to really learn these intricacies. But in general, we can then solve this equation using Abacus or the finite element software, and not to show off, but the solution matches what I did by hand. And this is the temperature at time equals 0, at time equals 0.1, and so forth. So the temperature is varying over time. You can see that here, the temperature is varying over time. And the temperature here is varying over time. For node number 1 and 2, 3, 4, 5, 6, it's been shown here that the temperature is dropping over time. And you can check to see if it makes sense, right? You have the boundary conditions. It's saying that the temperature forever is 0 at x equals -1. The temperature is forever equals 0 at x equals 1. So clearly we're fixing those temperatures at 0, while in between is parabolic distribution temperature. So it makes sense that the temperature is dropping over time. And you can see that the temperature here is parabolic. It starts at 0 and increases and then drops off. And that's clearly parabolic. And over time, it's changing over time as well. So very cool. So with that said, I'm going to move into thermal protection system. This is a basic course in heat transfer that I'm going to now take. And I covered finite elements. So I covered 2 topics into one: heat transfer by itself, finite elements by itself, and now I'm going to cover thermal protection systems so you can get an idea of where that is used. So thermal protection systems, I'm borrowing materials from 3 different sources. All these materials can be found through online sources, and I recommend you download them and look at them carefully. I think it's worth it. This is a very good document that talks about thermal protection systems, analysis and sizing for space plane configurations, and talks about the preliminary design of the TPS and the optimization of the insulation layer. And this is written by the Delft University over there, and it's a great document. I recommend you look at it. The objective is to minimize thermal protection system mass while ensuring that the material failure modes are well understood and the environmental conditions leading to failure will not be encountered for the selected mission. So what you want to do is you want to use low density materials, which tend to be better insulators than high density materials. You want to use high density materials which are better ablators than low density materials. Ablation is good. If you're losing material, is good because that's absorbing energy. Too much ablation may not be good because it can change the shape of the structure and influence the aerodynamics. Secondly, if you have too much ablation and the material is getting lost to the point that you could have a structural failure. Thermal protection system selection involves a balance between looking at good ablation amount, looking at insulation, and within that, we want to look at performance and manufacturability. We want to select the lowest density material that can handle the range of environmental conditions, heat flux, pressure, shear, and atmosphere. The material has to provide effective insulation for the imposed heat, and procedures for material fabrication, installation, and inspection should be established and preferably demonstrated. Very important consideration. For low heating environments, less than 20 to 40 watts per centimeter squared, we're looking at non-ablating, very low conductivity. You can even look at reusable materials. You can also look at conduction control by coatings to decrease convective heating and increase re-radiation. You also can look at situation where you have higher heating environments, as high as 50 to 200 kilowatts per centimeter squares. In those cases, I'm looking at ablative materials, which are really required. Conduction is controlled by including energy loss due to the ablation process, and that's important. You know, you're basically controlling the heat by ablation, actually. For both reusable and ablative TPS, a high emitting surface is desired to promote re-radiation. In other words, you want to have a surface that can emit really well. And you can do that. And that way you can also have heat being removed from the system. Ablative materials for heat shield designs are typically composites. Composite materials are typically made of two or more constituent materials with significant different physical or chemical properties that when combined produce a material with characteristics different from the individual components. The individual components remain separate and distinct within the finished structure, and a lot of the reinforcement materials you may encounter are going to be like carbon, glass, and or organic polymers that can react with the flow field gases to oxidize, melt, or sublimate. And matrix materials are going to be typically resins such as phenolics, silicon, and those react and decompose when heated. And it will lose mass in some cases and expel some gas. You're also going to have carbon behind being left, which is the charring process. Just to show you a little bit more, if you have a structure that's flying in the air and this structure has a backup structure. So I'm looking at a cross section, by the way. And this is the outside air, so free stream. And this is the backup structure. And this is the insulation material. So the blue and whatever you see here. So the point I want to make sure is that you understand that this structure is flying on the air at high speed, say, for example. And when exposed to atmospheric entry conditions, the surface here is going to heat up. And the heat is going to get rejected in two ways. You have re-radiation from the surface out, okay? And some of that will go back in through conduction. That makes sense. You also have convection flux going in, okay? And if you have the flow developing, you're going to have a boundary layer or shock layer. You're going to have a high emissivity coating. You want to emit a lot possible so you can have radiation out. And then you're going to have a low conductivity material here, which is in blue, to help you so that the heating does not go through quickly. Because you want to keep the backup structure as cold or as safe as possible. If you have astronauts inside, I want them to keep them safe. So I don't want this backup structure to heat up. So I need to design this material such that it doesn't heat up too quickly uh, in the cabin area, right? Reusable thermal protection systems are designed to reject as much heat as possible, right? And conduct as little heat as possible in order. So, right, that's what we talked about. We want to conduct as little heat as possible here, re-radiate as much as possible there, and that's going to help us get where we need to go. The high emissivity and low thermal diffusivity are desired in designing a TPS. Conduction within TPS materials depends on a lot of properties. You have thermal diffusivity comes into play, density, you have thermal conductivity and specific heat. If you want to come up with a formula that puts everything together, thermal diffusivity, if you put the conductivity of the material here, density here, and specific heat, this tells you how quickly the material will conduct, like a global quantity. It's very nice, very compact. High emissivity coatings increase the re-radiated heat flux and decrease the amount of radiation that goes into the material. So I want to explain some things that happen that are quite complex within this blue region for high heating applications. So when exposed to atmospheric re-entry conditions, heating conditions, the material will paralyze, it will char. So this, you're going to have a lot of char here. You're going to lose some material potentially, and you're going to reject heat by pyrolysis, blocking in the boundary layer, and formation of the char layer and re-radiation. So what you see here is that the black here, and pardon me, the black here has been, that surface has been eliminated, has basically ablated away. So you have mechanical erosion occurring from that. And then you still have the material decomposition. This material beneath is decomposing. You have char here, and then you have the material that has not experienced much yet. So we want to keep that as cool as possible to keep the structural material as cool as possible for the cabin, where the astronauts could be, or the payload or whatever you're looking at. But here's where all the action is happening. Again, ablation char, which is pyrolysis. There's a lot of activity going on here with gases getting expelled. You can see here when you heat up a structure at high temperatures, you're going to expel gases, particularly resin. And yeah, so that's kind of what we're talking about here. Very simple. And here I have a better picture if the previous picture was not helpful. And yeah, you have the ablating surface, the char, ablated already. I'm not sure what got ablated. You have the char zone, the decomposition zone, the virgin composite. And the polymer in the composite begins to decompose and paralyze. And the carbon will remain within the char layer, which, you know, you're going to have some amount of dark matter there. This thermal front is going to move through the material, causing this right here, this paralysis zone. The more you heat it up, the more it's going to move through the material down deeper and deeper, right? So as the mission, the launch vehicle is taking off, or the reentry vehicle, like the space shuttle, for example, is reentering, or you're looking at nozzle materials, this is going to keep moving down. What we want to make sure is to keep the structure cool. That's really what we want to do. And so the equations that typically looked at involve evaluating, the equations typically tackle the virgin, the char, the recession rates, you know, how quickly we're receding, losing material, thermal conductivity, and it evaluates the connectivity between properties. So it's going to look at how strength could be influenced by the conductivity, for example. But here are some of the variables that we start introducing. But you can see here, these are heat fluxes that are being considered, mass losses at the surface. And what we want to do is then look at the key properties needed to do an analysis this complex. That kind of analysis requires a good thermal response model. It requires a good thermal structural analysis model, and is going to require measuring density, thermal conductivity, specific heat, emissivity, and solar absorbivity. And you're going to do that for the virgin and char materials. You have the elemental composition, the virgin and char, You have the thermal gravimetric analysis. And then you're going to have to also simulate the porosity and gas permeability. You also have to have modeling that looks at heat of combustion and heat of pyrolysis. From the thermal structure analysis standpoint, we're looking at strength modulus, strain to failure, both at tensile and compressive loading, shear, Poisson ratio, and TPS. So you have to do a tremendous amount of battery of tests to fully formulate the properties you will need for the modeling of these kind of structures. And that takes a lot of work. And a lot of this stuff needs to be you need to measure it, because if you don't measure it, those are the inputs to the model. And so if the model is insufficient, we have a problem, right? If the model is using fake properties or assumed properties that are not correct, we have a big problem, right? And so, yeah, so that's what we got there. The design. So typically the design involves an integrated approach that combines mission requirements, the aerothermal and aerodynamics environments, a good selection of structural materials, and the ability to service the components. Also, we want to make sure we have good safety requirements. So a good test that's done on the ground to test the materials at hand is called the Arcjet testing. It's one of the best ground-based methods for evaluating the material response, ablation, and oxidation in a reentry environment. A material oxidation behavior occurs when heated in static or flowing air at ambient temperatures, pressures, and is likely to be significant during reentry environments. In a reentry environment, you're going to have oxygen and nitrogen, which could be dissociated. Catalyticity of the material also plays a role. A recombination of oxygen and nitrogen atoms can also occur at the surface that's been heated. And then you have the stagnation pressures that could be less than 1 atom. So those are the things to be considered for that. The Arcjet test is a very powerful approach. You can download the paper here. It's very old technology, and you can study that. But you have argon gas being used, you have air and nitrogen, and you have gas temperatures up to 12,000 degrees F with a DC power, and a cooling tower water because you don't want to damage everything. And so this has a nozzle that expands, and it's going to have high energy flow at Mach 5 or 7 with very high energy, megajoules per kilograms, being pointed and directed at a test article. So this test article is your material that we're trying to study. So this kind of material. And the idea is to look at the performance of that material. It can help you anchor analysis to test to make sure analysis that's using these thermal response models and thermal structural models are accurate, because those models will then be used to analyze a flight trajectory you may have. And so that's an important aspect. The plasma temperatures are generated by this electric arc, and they're accelerated into a vacuum chamber onto this test article. So very important, it's a vacuum test chamber, and it simulates very high altitudes, by the way. So one thing I want to point out, in this char region, we don't want to really lose this material mechanically. We want to retain the integrity of this char layer, because that char layer is helping me a lot. It's acting like an insulator, first of all. You have pyrolysis gas escaping, which is helping me with heat being removed from the system. But if I now remove this pyrolysis gas layer, this char zone layer, then I'm going to now encounter this virgin composite. This composite that has not been affected by this pyrolysis gas. And I don't want to get there. I don't want to lose mechanical this material, because now the heating gets applied directly into the virgin composite, which now will accelerate damage into the substructure. So we don't want to do that. We want to keep the char layer as intact as possible to be successful moving forward. The arc plasma facilities, there's one at the NASA Ames facility, has been used over 40 years to study thermal protection system material performance. There's two classes: low enthalpy, high pressure, high heat flux, high enthalpy, low pressure, low moderate heat flux. And it has significant flexibility. You have pressure, you can look at flow rates, test article designs, nozzle geometry, and so forth. There's a lot of flexibility. And you have the capability of simultaneously modeling representative flight conditions. And so there's good capability there. Challenges with thermal protection systems is that typically thermal protection system design sizes the material thickness to limit bond line temperature to a predefined maximum temperature limit. So if I have a thermal protection system on a launch vehicle that's bonded onto the composite, say, to protect it from the ascent environments or reentry, I want to make sure that thermal protection system is sized sufficiently of thickness, good material thickness, good enough to limit the bond line temperature, because you don't want to burn the composite beneath, which is a structural component. You don't want the temperature of the bond line to be higher than what the adhesive can survive. If bond line temperature is the design criterion, then you really need an accurate model to model these things accurately. The flight environment in a lot of cases are not accurately modeled. You don't have good understanding of those. The mathematical models may not be mature. Maximum bond line temperatures off is based on limited value. You have to put a value on the maximum bond line temperature. And you want to make sure that we have a good understanding of the flight environments. Those two things are important to size the TPS thickness. So very important consideration. Mathematical models that adequately represent materials physics and chemistry can be extrapolated to flight with some confidence. So we can use that. Once we can validate these models against Arcjet testing and other testing, we can then use those to extrapolate and look at situations that are outside of the range of ground tests and outside of the assessments that could look at design margins as an example, including factors of safety and things like that. So here is a list of thermomechanical properties, a very extensive list. I encourage you to pause the video and kind of look at this list, but it requires an extensive amount of material development, model development, and it requires performing TGA, various tests across industry are required, looking at how the composition of the virgin material is, looking at heat combustion of the virgin material, looking at heat formation near the char, looking at elemental composition of pyrolysis gases, looking at specific heat of virgin materials as a function of temperature, measuring the thermal conductivity of the virgin material as a function of temperature, deriving specific heat of char from known compositions, deriving optical properties of char from non-composition properties, and that can be determined experimentally, and then measure the thermal conductivity of char as a function of temperature. A lot of stuff needs to be done. And by the way, composites tend to be materially dependent. The directions depend. Uh, the materials have a directional dependency. I apologize for rambling there for a second, but we want to look at measuring the conductivity in the different directions because they're going to be different for composite. I really recommend reading this paper. It's called Development and Verification of the Charring and Blading Thermal Protection System Implicit System Solver. And I do think this paper goes into extensive derivations for and verification of what they use for the equations for modeling the heat and mass transfer in 3D for charring thermal protection system, including how to model pyrolysis. And it uses very similar techniques we discussed today, which is using the weak form of the problem. I showed you how to do that. We start with the governing equations. We multiply by a function that's unknown. We make it orthogonal to that. We assume an approximation over the domain, which is polynomial, and then we discretize the PDE, the partial differential equation, and we turn that problem into KU equals F. And we added a time-dependent problem, which we need to for this kind of problem, and we can then solve it. Basically, we can time march the solution moving forward or backward difference, but you have to really look at the temporal and spatial behavior of the solution, because this is very important when sizing a structure. insulation material. The TPS model has to account for the effects of surface recession, surface temperature, bond line temperature, char thickness, and char depth, in-depth temperatures, and the models have to allow for TPS design, material stress studies, TPS mass estimates for system analysis studies. Just to show you how complex this is, I'm showing the 1D governing equation. This 1D governing equation shows how you have to tackle the various aspects, the pyrolysis gases aspects, the convective heat transfer, the convection, and so forth. And I want to go through each term. So here is the convection term. Looks very similar to what we talked about before. You have the radiation term, which is going to account for radiative heating. So the hot gas itself can radiate heat into the material. Then the re-radiation, which is going to have the Stefan-Boltzmann coefficient here, epsilon, and then you have sigma here. So these are constants, and now you have this re-radiation term. Then you have the wall mass flux at the wall. You're going to lose some mass potentially. You're going to have some char, some mass loss from char. You're going to have some gas flux. And you have to have these three things in equilibrium. Mass has to be constant. So whatever is lost and anything in has to be constant or equal to zero. Then you have the conduction aspects. So all this has to be accounted in these equations. And then you have to add the energy equation and the gas continuity equation. Those four equations together for 1D need to be solved. So a lot of times these problems, which may be three-dimensional in nature, sometimes are solved in a one-dimensional manner to solve the problem, to basically accelerate solving the problem as much as you can. So with that said, this gives a very top-level view of a thermal protection system problem. We'll be doing some of that in a project. We'll be looking at how we can size the thickness. You'll be looking at that. But we're going to try to not focus on these other terms that could be quite complex, but maybe like a first order estimate of what that would look like. With that said, I want to open the floor. And so I'm opening the floor to explain to you that this model is not simple. The thickness can change over time. It's a time-dependent problem. There's radiation included, the convection is included. And all this, a lot of this stuff is also coupled to the fluid mechanics as well. How fast the vehicle is moving, and what is the boundary layer really doing there. And so there's a lot of aspects coming into play, what the materials are doing in terms of chemistry, decomposition, and so forth. I really thank you for watching this particular lecture. I think we will then apply that to a real problem. That is the goal.